Hello friends, you are welcome for the IDMT over current relay, its working and construction. The content of this lecture are basics of induction relay, types of induction relay, torque development, construction, plug and time setting, technical specification, and the calculation of plug setting and the time multiplier setting. So this is the photograph of 2J-M10 Essen re-roll 2 overcurrent plus 1 earth fault IDMT relay. This is the combined unit 2 OC plus 1 earth fault relay. These overcurrent relay and earth fault relays, they are also available in the single element or single pole construction also. Now we start with the induction type relay. So this electromagnetic induction. Okay, so it is based on the induction principle, which works on the mutual induction like transformer, induction motor, and because of this mutual induction, the torque is developed on the rotor or the disc in the induction relay. So this is the operating principle like transformer action or the induction motor action. So the torque is generated in the disc on the principle of induction. So this relay works on the alternating current, okay, and it deals with those relays. They are simply called as a induction type relays. Okay. So this torque is produced in these relays when one alternating flux reacts with the current induced in the rotor by another alternating flux. Okay, means to generate the torque in the disc, we required two flux. Okay, like in three-phase induction motor, there are RYB three phases. Okay, so in this case, we are sensing the current from R phase, Y phase, B phase separately, but to generate the torque on the aluminum disc, we required two alternating fluxes. Okay, so that we'll see in the details. Okay, so there are two types of the induction relay based on the structure. Okay, first one is called as a shaded pole structure. Second one is a watt hour meter type structure like energy meter, and third one is a induction cup type structure. Okay, so these are the three types of the induction type relay based on their construction. There are three types. So depending on the type of rotor, whether disc or cup, the relay is known as the induction disc type or induction cup type. Okay, means for the torque generation, what kind of shape we used, okay, whether it is a disc or cup, based on that these relays, they are called as a induction disc type or induction cup type relay. Okay. So these high, low and adjustable speeds are possible, and various shapes of time operating quantity curves can be obtained. Okay. So depending on the various characteristics, that is Ni, normal inverse, very inverse, extremely inverse. Based on this operating time, there are various curves, and for these various types of curves, on the operating time, these speeds can be adjustable, and accordingly these relays, they are designed for the current coils. Okay. Then the most common type of relay is an induction disk type relay, which is used most commonly in the protective relays. Okay. And second one is a shaded pole type. Okay, shaded pole type. Okay. And the watt metric. So in this aluminum disc type construction, there are two relays. One is shaded pole relay, and this is a watt metric type relay. Okay. First we'll see the shaded pole relay. The shaded pole structure, okay, it is shown in this figure. So this is a shaded pole relay. On this vertical limb, the actuating quantity or the coil, it is wound. There is a small air gap between the magnets on the other side, and in this small air gap, this aluminum disc, it is mounted on this moving system. This pole of this vertical magnet, so this shading ring, it is provided. Shading ring, it is provided. Okay, so this shading ring is made up of copper or the aluminum. The function of this shading ring is to generate the two fluxes in this air gap, and these two fluxes, they linked with this aluminum disc, and they will generate the phi 1 and phi 2 two fluxes. Okay, so these, say phi 1 is the shaded pole flux, and phi 2 is the non-shaded pole flux. Okay, and because of this shading ring, this flux phi 1 in the region of shading ring, which will lag to this phi 2 non-shaded pole, and in this way this phase difference, it is achieved in the shaded pole type structure. Okay, so to generate the torque, this shading ring type structure, it is used. Then in the watt metric type structure, there are two magnets. Okay, one is called as a E-shaped magnet and another one is a U-shaped magnet, or it is called as a upper magnet and the lower magnet. Okay, so on this upper magnet, the current coil, it is provided, which is connected to the secondary of the current transformer, and one secondary coil, it is provided on the same limb of the upper magnet, and this is linked with the lower magnet. Okay, and because of the inductance of the two circuits, okay, so this flux, they are generated by this upper magnet and this lower magnet, or primary coil and the secondary coil, and because of this resistance and inductance of these two coils, it is a different, and the phase angle, it is generated in the two fluxes, and these two fluxes, they linked with this aluminum disc, and the torque is developed on this aluminum disc. Okay. So this is the watt metric structure. Now for this both relays, normally the relay contacts, they are operated directly by an arm mounted on the moving system or the rotor of the spindle. So when this torque it is generated in this aluminum disc, so this contact moves and it will bridge the gap between this moving contact and the fixed contact. Okay. Then the distance of travel of the arm carrying the bridging contact to the relay contact can be adjusted with the help of the time multiplier setting. Okay, means the travel or this angle theta can be set by changing the distance or this reset position of this aluminum disc. Okay, so various steps they are provided on the current coil on the upper magnet, so that we can set the various percentage of the rated current on the relay. Okay, so we can adjust this various percentage of setting or plug setting by inserting the plug. Okay, so this is known as a plug setting multiplier. Then the permanent magnet is provided to give the eddy current braking to the disc. Okay, like in the measuring instrument, we are providing the torque development system, we are providing the controlling system, and we are providing the braking or damping system. Okay, in the similar way, so in this induction type relay, the permanent magnet it is provided to give the braking or to give the damping or to give the steady state speed for this disc. Okay, so this is necessary to reduce a minimum overrun of the disc in case current or voltage providing the driving torque stops before the operation has been completed. Okay, means for that we'll see, once the fault or abnormal condition it is sensed by the relay, so it will generate the torque or it will develop the torque in the aluminum disc, and so this disc it starts rotating to close the contact, and before closing the contact the fault is get isolated. Or suppose it is a momentary fault and this fault is removed from this system, and because of this inertia of this aluminum disc or the moving system, after getting clear this fault, if this disc moves in the same direction and it closes the contact, this fixed contact and moving contact, so it will give the tripping command to the circuit breaker. Okay, and after clearing this fault, if it gives the tripping command, so that is a malfunctioning or the maloperation. Okay, And in this case, so the large area is get disconnected even when there is a healthy condition. So to avoid such a type of operation, this braking magnet is provided, and on the outer periphery of this disc, the slots, they are also cut. Okay, means as the speed of disc is more, so your braking torque TB, it is proportional to the speed square. It is proportional to the speed square. Okay, means when this driving force or fault current, it becomes zero, then your torque developed in the aluminum disc, it is zero. But because of this inertia, because of this speed, so it should brake immediately. For that, this braking magnet is also provided. Okay, so this overrun is not more than 2 cycles. It is not more than 2 cycles, or it will interrupt on the interruption of 20 times setting quantity. Means when there is a fault current is of 20 times, then the set value, and in that case, so only 2 cycles overrun, it is allowed. It is allowed. Okay, means fault clear होने के बाद only 2 cycles it is allowed. Means only 2 cycles means for 2 cycles means for 40 milliseconds. So this disc is moved in the forward direction, and within this 40 millisecond, so this braking torque, it should be applied on this aluminum disc, or the disc should stop rotating when this fault current is get cleared. Okay, so this is called as a overrun function, and for that the braking magnet is provided. So this is a 2TJM10 2 over current earth fault relay. This is the previous photo is with the total assembly. So this outer portion, it is a housing of this 2OC1 earth fault relay. This is overcurrent element. So these are the 2 overcurrent element, and this is a earth fault element. So this is an open structure. So this relay, they are generally these relays, they are draw out a type for testing purpose. Okay, so depending on the relay placement in the power system, so we can test this relay half yearly or yearly. So to test this relay, so we can take out this relay from the housing without disconnecting the connections of current transformer, potential transformer, or the tripping circuit connections. Okay, so for that purpose, so this is a draw out type relay. So we can take out a relay from the housing, and we can test this relay individually. So this is a torque development in the shaded pole type relay. So here this is a phi 2 non-shaded flux, this is a phi 1 shaded flux, and these two fluxes phi 1 and phi 2, they will interact or they will link with this aluminum disc, and this phi 1, because of this phi 1, the EMF is induced in the aluminum disc, and because of this induced EMF, so this I phi 1 current is generated in the aluminum disc. Okay. So this I51, it interact with the flux phi2. Okay. Similarly, this flux phi2, it links with the aluminum disc, and because of this flux phi2, EMF is induced, and because of this EMF induced, this I phi2 flux, it is this I phi2 current, it is flowing in the aluminum disc, and there is an interaction of this I phi1 current because of this flux phi1 with phi2, and because of this interaction, so this force is induced in the aluminum disc. Similarly, because of this I phi2, it interact with this flux phi1, and this force F1, it is developed. So in this way, the torque is generated in the aluminum disc. Here, this is for wet metric type relay. So this is a phi p upper magnet pole. This is the lower magnet pole. Okay. So this is a closed coil, secondary coil. So it is connected with the lower magnet, and because of this flux phi p, the current is induced in this secondary coil, and this current is moved or flowing through this coil. And because of this current in the secondary winding, so phi s in the downward direction, phi s in the upward direction, these fluxes, they are generated. So this can be found out by using the right hand rule or by using the corkscrew rule. So here, based on the direction of current, flux phi s, it is in the downward direction, flux phi s in the upward direction. Okay. So these fluxes, they linked with this aluminum disc, and this is a current because of this phi s. Okay, secondary current. Because of this phi p or the primary current, so this phi p, it is linked with this aluminum disc, and there is a IEP eddy current induced in the aluminum disc. So these currents, they will interact with this flux, and this torque, it is generated in the disc. Because of this phi p, IEP is there, and it is linked with this phi s of this secondary coil, and the torque is generated. And based on this, the resultant torque of this IES and IEP, the resultant torque is generated in the aluminum disc, and it starts rotating. Okay. So this torque TD, it is a proportional to phi p and phi s sine of alpha. So this phi p and phi s, this is these fluxes, they are generated because of this current I flowing through this primary winding, and this total torque TD, it is a proportional to, say, phi p and phi s, and angle between these two sine of alpha. So this phi p and phi d, they are developed because of the current flowing through this primary winding. So it is a proportional to I square sine of alpha. Sine of alpha. Okay. Means as the magnitude of current, it is increases, so the torque is developed in the aluminum disc. Okay. So this is a torque equation of the induction type relay. So how this relay, it operates when there is a abnormal condition. Okay. So as the fault impedance is less. When there is a fault in the system, the impedance of fault, it is less than the load impedance. And because of this, the fault current is more than the load current. Okay. So this fault current, it depends upon the magnitude of fault impedance. Okay. If your fault impedance is less, so your fault current is more. Okay. If short circuit occurs, in the circuit impedance is reduced to a low value, therefore fault is accompanied by large current. Okay. Short circuit हो गया means क्या हो गया? So current is flowing to the unintended path, and for that the impedance of the fault, it is reduced, and the large fault current, it is flowing through the system. So this overcurrent relay, they will sense this fault current, and if there is a overload condition, that overload current is also sensed by this overcurrent relay. Okay. So this overcurrent protection is that protection in which the relay picks up when the magnitude of current exceeds the pickup level. Okay. Pickup level means the set current. Okay. When your fault current, it is more than your pickup current or the set current, the current is more. So this more current, it will generate the torque in the aluminum disc. Okay. So the disc, it is a start rotating. It starts rotating. Okay. So the basic element in this overcurrent relay is in overcurrent protection is the overcurrent relay. Okay. So this total mechanical assembly, including the upper magnet, lower magnet, primary coil, secondary coil, aluminum disc, moving system. So this total is called as a overcurrent relay. So here, this is another view of this overcurrent relay. Here we can set the relay, or we can set the pickup current. Okay, so this is called as a plug setting. This is called as a plug setting. Here we can set the time, operating time of the relay. So this is the time multiplier setting. Okay. Here we can see this. This is a aluminum disc. This vertical, it is a moving system. Okay. Here these are the various terminals they are provided to connect the city secondary, to connect the trip circuit, to connect the alarm circuit. Okay. Now we'll see the various parts of this relay in detail. Okay. So there is a primary winding with tappings. Okay. So this part, it is a primary winding. Okay. So this primary winding, it is having 7 tappings. It is having 7 tappings. Okay. That we'll see in detail. Then there is a secondary winding. So on the same pole, the secondary winding, it is provided, and the other terminals of the secondary winding, it is wound on the lower magnet. So there is a closed loop circuit is there. So there is a closed loop circuit is there. So when this flux, main primary flux, they are flowing through this upper magnet, and because of this flux linking with this secondary winding, so EMF is induced in the secondary winding, and the circuit, it is a closed, it is a complete. So this IS secondary current, it is flowing through this secondary winding, and because of this current, so the flux phi s, it is developed and linked with the aluminum disc. Okay, so this is phi s, and these are the primary flux phi p. Okay, so these two fluxes phi p and phi s, they are linked with the aluminum disc, and the torque is developed in the aluminum disc. Then next is fixed contact. Fixed contact. So this is a fixed contact. Okay, here this 3 number, it is a fixed contact. Then 4th number is a moving contact. So this moving contact means it moves with this aluminum disc or this moving system, and it will bridge the gap between this fixed contact. So it is called as a moving contact. Okay, here this is a moving contact. When aluminum disc moves in the clockwise direction, so these 3 number and 4 number, they bridge the gap, and the contacts, normally open contacts, they becomes closed. They becomes closed. Okay, so in this way there are set of the contact. One is fixed contact and moving contact. Then next is a upper magnet. So this is E shape, is a upper magnet. Lower magnet, U shape, is a lower magnet, where the secondary winding, it is provided. On the upper magnet, there is a primary winding with tappings, there is a secondary winding is provided. Okay. So these magnets, they are laminated to reduce, to minimize the iron losses, to minimize the eddy current losses. So they are laminated. Then this AB, from this fixed contact, they are connected to the trip circuit. They are connected to the trip circuit. Okay, so these are the parts for the watt metric type relay, induction type relay. Okay, for this shaded pole induction relay, so here there is a aluminum disc. This 3 number is a fixed contact, 4 number, it is a moving contact. Here there is a primary winding which is connected, which is having the different tappings and connected to the city secondary. So this is a braking magnet, permanent magnet. Here there is a shading coil or shading ring, it is provided, and this vertical is a shaft or moving assembly. Okay, on this magnet, so here this is a main coil. Okay, so these are the various parts of the induction type relay for watt metric type and the shaded pole type construction. Now we'll see this construction in detail for watt metric type relay, which is most commonly used in the protection system. So here there is a upper electromagnet. So this is an actual view of 2TJ 10 2OC 1 earth fault relay. Okay, so here you can see this is the upper magnet. This is a upper magnet, and this part, it is a lower magnet. Okay, so these are the two magnets they are laminated. So this upper magnet is one of the primary winding connected to the CT secondary. Okay, so this black portion, it is a primary coil which is connected to the CT secondary through this black sleeve wire. Okay, so you can see this black sleeve wire, it is connected to the CT secondary. Then the tappings are connected to the plug setting bridge. Okay, now you can see in this coil, so there are number of wires they are provided. See, this is a gray, red, green, yellow, black. So these wires, they are taken out from this coil. So the various settings that can be achieved, and there are n number of turns, and from this n number of turns, okay, so after say n1, n2, n3, after some fixed number of turns, these tappings, they are taken out and they are connected to the plug setting bridge. So with the help of this, we can set the desired current on the relay. Okay. The secondary winding is energized by the induction form. The primary, it is connected in series with the winding on the lower magnet. Okay. So from this upper magnet, so few turns from this coil, they are separately wound on this bobbin and they are connected through this black and through this red wire to the secondary winding mounted on this lower magnet. And the secondary winding is energized by the induction from the primary winding. Okay, so they are mounted on this end. So there is a induction effect, and because of this induction effect, the current is induced on the secondary winding, and it is closed loop. Okay, it is closed loop with this lower magnet. So circulating current, it is flowing through this secondary winding. Okay, and they are connected in series with the winding on the lower magnet. Okay, so in this way, these windings, they are placed on this upper magnet, lower magnet. Because of this primary current, the current is induced on the secondary winding. Then after that, there is a aluminum disc. It is mounted between the air gap of these two fluxes. Okay, so you can see here, this is the slotted aluminum disc. This is a slotted aluminum disc which is placed in the air gap between upper magnet and lower magnet. So this arrangement, the leakage fluxes of upper magnet and lower electromagnet are sufficiently displaced in the space and in phase to set up the rotational torque in the aluminum disc. Okay, so as you see, the size and the number of turns on the both coils. Okay, so depending on the n number of turns and the cross-sectional area of the conductor, in two coils. Okay, So based on the number of turns, the cross-sectional area, the resistance of both coil, it is different. The inductance, it is different. And because of this, the inductive reactance of both coil, it is different. And because of this inductive reactance, say phi P, because of this primary coil, and phi S, the secondary coil flux. Between these two, phi P and phi S, there is a certain phase angle. There is a certain phase angle. Okay, so this is decided or designed at the time of designing this coil or of the relay. Okay, so because of this phase angle or phase difference between phi P and phi S, they linked with the aluminum disc, and the torque is generated in the aluminum disc. Okay, so to develop the torque, so this phi P and phi S, the phase displacement, it is created to develop the torque in the aluminum disc. Okay, so that is depend upon the resistance and inductance of these both coils. Okay. So these two alternating fluxes, they cut the disc and produce the eddy currents in it. Okay. So the torques, they are produced by the interaction of each flux with the eddy current produced by the other flux. Okay, means say I E eddy current, because of the secondary winding, it links with the primary flux. It links with the primary flux. And interaction of each flux with the eddy current means this phi P is interacting with IES, and this phi S secondary flux, it is linked with the eddy current generated because of this primary winding. Okay, so because of this interaction, this torque is generated in the aluminum disc, and the resultant torque causes the disc to rotate. Okay, so in this way, this torque is generated in the aluminum disc. The spring is provided on the moving system. One end of the spring, it is a fixed, and other end it is connected to this moving system. Okay, so the spring provides the resetting torque. It provides the resetting torque, means when the torque is developed in the aluminum disc, it moves, it rotates, and it closes the contact, so it must come to its original position. Okay, or after getting clear the fault, the disc or this torque should be reset. So for that purpose, this control spring, it is provided. Okay, then the magnet, permanent magnet, is employed to produce the eddy current breaking in the disc. Okay, so that we discussed. The breaking torque is a proportional to the speed of the disc. Okay, means to cut the permanent magnet flux, the slots, they are provided on the outer periphery of the aluminum disc, and as the speed increases, so your breaking torque TB, it is increases. So it is a proportional to the speed. Okay, it is a proportional to the speed. So in this way, as the speed increases, so your breaking torque also increases, and when the fault, it is get cleared before tripping or operating of the relay, so the breaking torque is more, so disc is stopped within 2 cycles. Within 2 cycles. Okay. So here you can see this is a say picture from the downward side of this relay, and here you can see this is a permanent magnet. There is a small gap, and this is a slotted aluminum disc. Okay. So this braking system, again this we discussed. Okay. So braking is provided within the 2 cycles at the fault level of 20 times the set magnitude or the set current. So here there is a controlling spring, and when the operating current or the fault current which exceeds the pickup value, so this driving torque, it is developed or it is produced in the disc, and it accelerates the aluminum disc. Okay. So this rotation of the disc, it is a proportional to the driving torque. Okay. So the current, when current it is below the pickup value or below the set value, so in that case the disc should remain in the stationary condition, or it remains stationary, or it remains steady. So for that the tension, it is given by the controlling spring. It is given by the control spring. Okay. So this control spring, it acts against the normal direction of the disc rotation. Okay. If the disc, it is moving in the clockwise direction, so this spring, it is providing the opposite force on this moving system, so that when the current, it is below the pickup value set current, so your disc, it is in the stationary condition. Okay. So the disc rests against this backstop. Okay. अभी ये जो कंट्रोलिंग स्प्रिंग है उसकी वजह से, so the force it is acting on this aluminum disc, so this disc is start moving in the anti-clockwise direction. Okay. So for that purpose, so there is one home position. There is one home position for this total moving system. Okay. So that is called as a backstop. That is called as a backstop. Okay. So the position of backstop is adjustable with the help of this time multiplier setting. Okay. So we can change this backstop position or the travel of this aluminum disc. Okay. So that the relay contact's travel distance can be varied according to the need, and that's why it is called as a time setting relay. Okay. So in this way, on this induction type relay, we can set the operating time. We can set the operating time, and we can set the operating current. Okay. So because of this, we can set the IS, we can set current, and we can set the operating time of the relay. Okay. So both facility, they are available in the relay. So here these are the some pictures of plug setting. Okay. There are some pictures of plug setting. Okay. So here, as we say, there is a primary winding with the tappings. So this is the primary coil, and these are the different tappings taken out from this primary coil. Okay. So this black and red these are the two wires connected for the secondary coil on the lower magnet. Okay, and these are the different tappings for the various currents. Okay, so these tappings, they are connected to the primary coil. Okay, and the plug setting bridge Okay, so this total assembly, this is called as a plug setting bridge. Okay, now from this front side we can change the pin position and we can set the various currents on this plug setting. So here you can see the wires from the primary winding, they are connected to the plug setting. Okay, so that you can see here. Okay, so in this way, this is the plug setting arrangement. By changing this white pin, we can set the current on the relay. For overcurrent relay, the setting is from 50% to 200%. Okay. And for earth fault relay, it is from 10% to 40% or from 20% to 80%. Okay. So by changing this pin position in these various slots, we can set the relay. Okay. So this is a plug setting arrangement in the induction disc type relay. Okay. So these are the various tappings taken out from the primary winding. So 50% to 200% at the step size of 25% for overcurrent relay. Okay, and from 10% to 70% or from 20% to 80% with the step size of 10%, 5% or 10% for earth fault relay. Okay, for earth fault relay, the magnitude of earth fault is very less, so we can sense this small amount of earth fault current. For that purpose, the setting range, it is less. Okay, the values assigned to the each tap, they are expressed in terms of percentage. Of full load rating of the current transformer. Okay, say 400 by 5 ampere, it is a CT ratio. So this is a IN on the secondary side. So we are expressing these settings in terms of full load current of the CT secondary. Okay, so here we'll see the example. Here CT secondary, it is a 5 ampere and plug setting, it is provided at 2.5. so here it is a 2.5, and from this we can find out the set current IS. Okay, so here IN, it is a 5 multiply by M1, so this is a value of M1 2.5 and multiply by M2, it is given 0.5. Okay, so depending on the various manufacturers of this relay, so this set current equation that may vary. Okay, so after calculating this, we get the set current of 6.5 ampere, 6.25 ampere. Okay, and this 6.25 ampere of rated current 5 ampere. Okay, 5 ampere का 6.25 ampere we set this current. Okay, and this is 1 125% of this IN. This is 125% of IN. Okay, rated current. So we set this relay at 125% of the rated current. 125% of the rated current. Okay. So in this way, we can find out the percentage setting, or we can set the various percentage with the help of this plug setting on this relay from 50% to 200% for overcurrent relay, and for 10 to 40% or 20 to 80% for earth fault relay. Sorry, here it should be earth fault relay. Okay. So in this way, we can set the relay as per the fault level of the system, fault level of the power system. Okay. So in this way, this is the function of the plug setting on the induction type relay. Okay. So here you can see directly it is given in terms of 2.5, 3.75, 5, 6.25, 7.5, 8.75 and 10 amperes. Okay, so directly it is given in terms of current. Okay, so 5 ampere का 2.5 क्या हो गया? So this is 5 ampere relay. This is 5 ampere relay. Okay, so 5 ampere का 2.5, it is a 50%. It is a 50%. And 5 ampere का 10 जो है, it is 200%. Okay, means this 10 ampere, it is a 200% of 5 ampere, and 2.5 is the 50% of 5 ampere. So in this way, we can set this relay from 50% to 200%. Okay. So this is the pin. Now we see the time setting multiplier, how we can set the time on the relay. Okay. So we can change the angle between 0 to 360 degree, and thereby we can give the desired setting. Okay, so this angle theta, we can set between 0 to 360 degree. Okay, so this is a fixed position of this fixed contact. So we can move this complete assembly or this moving system so that we can set the angle, or we can set the travel of this aluminum disc. Okay, so with the change of this travel, we can set the operating time of the relay. Okay, and this total adjustment, it is called as a time setting multiplier. This total adjustment, it is called as a time setting multiplier. Okay, so in this system, how we can move this total assembly? This reset position, it is called as a backstop. This is called as a backstop. Okay, so it is connected with this moving system. Okay, so you can see this vertical knob, it is called as a backstop. Okay, and with this backstop, so this horizontal needle of the moving system, it is a rest on this backstop. Okay, so this is a moving contact on this moving system. So this will bridge the gap between these two fixed contact. Okay, So by moving this backstop, we can change this time scale. We can change this time scale, or we can change the travel of this aluminum disc. Okay, so this is the time multiplier setting of the induction type relay. So here we can see how this time multiplier setting, or how we can change the travel. Okay. So here TMS is at 0.1, and you can see here this is a back stop of the moving system. Okay, so TMS at 0.1. So we consider this position as a TMS 0.1. Then we change this TMS, so we can move this disc in the clockwise direction, and we set this TMS at 0.5. Okay, TMS at 0.5. So you can see the position of backstop. So it is moved from this position to this position. Okay, then at 0.75, TMS is equal to 0.75. So it is a further move in the clockwise direction. So this is a position of backstop. So again it is moved in the clockwise direction. At TMS is equal to 1, so it is further moved. So we cannot see this backstop because it is moved on the backside. Okay, so as we increase the TMS, so this angle theta or reset position, it is increased. Okay, means as the TMS increases, so the time required to bridge the gap between fixed contact and moving contact, it increases. So in this way, by changing this time multiplier setting 0.5, 0.6, 0.7, 0.8, we can change the operating time, or we can set the operating time of this relay. Okay, so these time multiplier settings, they are available from 0.05 to 1 with the step of 0.05 Okay, now this 0 to 1, these numbers, they will not represent the actual operating time of the relay. Okay, they will not represent the actual operating time of the relay, but they are the multipliers to convert the time known from the relay nameplate. Okay, so for this relay, so there is a standard characteristics is there. Okay, and from that characteristics and the multiples of setting on this relay and the time provided by this relay. So this is also standard characteristics of this relay, and from which we can find out the operating time, actual operating time. Okay, so with the help of these figures, we can multiply with this operating time from the standard characteristics, and from that we can get the actual operating time. For that we will see that TMS is equal to 1. This standard characteristics, it is a defined, or it is given for TMS is a set at 1. And for this TMS set at 1, when there is a 2 times fault current, then the set value, so IS multiply by 2. So your relay is a trip at 10 seconds. 10 seconds. So 10 times of plug setting. So we are considering this example. When there is a 10 times current flowing through this relay, 10 times of plug setting or set value. So this relay, it trips in 3 seconds. It trips in 3 seconds. Now we change the TMS position to 0.7. So at this 3, we multiply by 0.7. So 3 multiplied by 0.7. So 2.1 second is the actual operating time. Now we shift this TMS at 0.5. So 3 multiplied by 0.5. So 1.5 second. Now we shift this TMS at 0.3. So 3 multiplied by 0.3. 0.9 second. Okay. So from this characteristics at this time multiplier setting, we can calculate the actual operating time of the relay. Okay, so for that purpose, this TMS, it is given. Okay, so it is not the actual operating time of the relay. So with the help of characteristics and this time multiplier setting, we can find out the relay. Then now we discuss about the housing and connection. This total relay, it is placed in this black metallic assembly. Okay, so which will provide the protection, mechanical protection for this internal part of this relay. Okay, so generally these relay, they are draw out type for testing purpose. Means this total assembly, it is mounted on the panel with the help of clamp, and if we remove the front cover and we take out this relay for the testing purpose, and at this back side the other connections of the relay, they are kept as it is. Okay, so this is the functioning of the housing. So on the back side of the relay, there are 6 terminals they are provided, or 3 pairs they are provided. To connect these 6 terminals to the current transformer. Okay, so there are R, Y, B, 3 cities are there, and to connect these cities to this element or to this relay, so 3 to the 6 terminals they are provided, or the 3 pairs they are provided to connect these coils to the current transformer secondary. Then 2 terminals they are provided, normally open contacts they are provided for these relays, protective relays. One set is for tripping purpose, which is connected to the trip circuit. Then next set of terminal, it is used for the alarm annunciation to show the overcurrent tripping, and when there is a operation on the overcurrent, so these contacts they are get closed and they will give the command to the alarm annunciation, which will give the indication of overcurrent fault. Similarly, the another pair, it is given for the alarm annunciation for this earth fault indication. Okay, for the earth fault indication. So in this way, the 12 terminals they are provided on the relay assembly and the back side of the relay housing. So these normally open contacts, they are self-reset. Self-reset means when the fault, it is isolated by the relay by giving the tripping command to the circuit breaker. Okay, so this circuit breaker, it isolate this fault. Okay, and the fault current through this relay coil, it becomes 0. So the driving torque on the aluminum disc, it is 0. So TD, it is 0. So because of this controlling spring, this aluminum disc come to its original position. With this, the normally open contacts they are also reset. They are also reset. Okay. So when there is a fault, so this normally open becomes close, and the gap or the tripping signal, it is given to the circuit breaker. Circuit breaker isolate the faulty section. Then fault current, it is 0. With this fault current, 0 fault current is flowing through this coil, primary coil. So this torque developed on the moving system, it becomes 0. And with the help of controlling spring, these output contacts, they are self reset. Okay. So the relay trip indication, it is given with the help of flag, and this flag, it is a hand reset. It is a hand reset. Okay. Means when the circuit breaker, it gives the tripping command, the relay operates, but the relay is operate, a relay is a trip, so that indication, it should be in the latch condition. Okay, it should be in the latch condition. Okay, so it is a continuously operated condition, and when the fault is rectified, so in that case, this flag, it is a reset by that operator, or it is a reset by that engineer. Okay, so that is called as a hand reset operation. So this is the housing and the various connections on the relay. So this indication is called as a flag. This indication, it is called as a flag. So this is a healthy condition of the relay. This is healthy condition of the relay. And when the relay trips, so you can see the orange flag on the relay. Here, this is normal condition. And when the fault occurs, so here you can visualize the red line on this relay. Okay. So this is called as a flag of the relay. Now here you can see this is a auxiliary contact. This is auxiliary contact. When the relay is in normal condition, so these contacts, they are open. They are in an open condition. When the relay operates, now you can see this gap between this contact, it is a bridge by this vertical bar. Okay. So this is a closed position of this contact. This is a closed position of this contact. And through this contact, the signal, it is given to the tripping command. The signal, it is given to the alarm annunciation system. Okay. So through these black wires, the signal or circuit, it is get completed, and it will give the tripping command, and it will give the alarm command to the. Okay. So here you can see these are the two contacts. So this is a bridging rod, metallic rod. Okay. So when this disc moves, so this gap or these normally open contacts, they are get closed, and they will give the tripping command to the circuit breaker. So these are the operating contacts or the auxiliary contacts of the overcurrent relay. At the back side, you can see the wiring. Okay. So from these CT terminals, two wires, they are get connected to these coils. Then these two wires, they are get connected to this tripping or the alarm contacts of the system. Okay. So all these CT connections, auxiliary contact connections, they are connected to the terminal block of the relay. So here you can see when we remove the relay from the housing. So with the help of this sliding contacts, they are get slide with the fixed housing on the panel, and they will provide the connection to this relay through the wires. Now when we take out this relay from the assembly, so we studied the CT secondary should not be kept open. Okay. So when we take out this relay from this housing, so these links they are provided. So when we remove this relay, so these links bridge the gap between S1 and S2 terminals of these three cities. S1, S2 terminal of these three cities, and the current is circulated through this shorted link. Okay. So when we insert this relay in this housing, so this black knob, say they will slide here. After connecting these terminals to this silver contact or to this fixed contact, so they will engage with this fixed terminals on the housing, and after some travel in the backward direction, so this black bakelite, they will open these links and current is start flowing through these relay coils. Okay. So in this way, these sliding contacts and these fixed contacts, they are connected, and relay is get connected with the CT secondary and the trip circuit. So at this back side here you can see these 12 terminals where we can connect the CT secondary, tripping circuit, alarm circuit for overcurrent, alarm circuit for the earth fault relay. So with the help of this brass clamp, we can fix this relay on the control panel from the back side. Okay. So this is a connection diagram for this 2TJ relay of Eason reroll. So here these are the normally open contact, 3, 4 normally open contact, 11, 12 normally open contact. This is a 2 overcurrent coil, 1 earth fault coil. Then 5, 6, 9, 10, 7 and 8. Here we are going to connect the relay element. So S1, S2, these are the CT secondary terminal. So all S2 terminals, they are shorted here and it is connected to the terminal number 7. It is connected to the terminal number 7. Okay. And the S1 of R phase, it is connected to terminal number 5. S1 of B phase, Y phase, it is connected to the terminal number 6 or 8 or 10. Then S1 terminal of B phase, it is connected to the terminal number 9. Okay. This star point, it is connected to the terminal number 7 and at the terminal number 8. Okay. So here the shorting link, it is provided. Okay. So in this way, the CT S1, S2 terminals, they are connected to the relay. Okay. So this symbol, it is providing or it is showing the shorting link of the relay. Okay. So here the 3 4, it is a tripping contact for overcurrent as well as for earth fault. Okay, so this is overcurrent element, this is earth fault element. So when the fault is in overcurrent or earth fault, so both they will give the tripping command through this 3 and 4. When there is a overcurrent, C1 and 2, it is given to the overcurrent alarm annunciation. When there is a earth fault, so 11 and 12, it is given or to the alarm earth fault alarm annunciation system. Okay, so in this way, this relay, it is connected in the CT secondary side or on the tripping circuit or the alarm annunciation circuit of the relay. Here, this is the another make of the 2 overcurrent 1 earth fault IDMT relay. These are the single element overcurrent relay. So this is the normal inverse 3-second curve NI3 means when the 10 times fault current is flowing through the primary coil 10 times than the set current or I pickup current. Okay, so this relay trips in the 3 seconds. Okay, so that we can verify from this coil. So in this characteristics, on y-axis the time it is given, and on the x-axis the current. Directly current it is not given, but it is given in the multiples of plug setting. Means 50 to 200% के सेटिंग में या फिर आपका जो ISS सेट करंट है उसके मल्टीपल्स में that we can find out. Okay, means when there is a fault current flowing through the primary side, that fault current it is flowing through the secondary side of the relay coil. This fault current ये आपके सेट करंट के कितने मल्टीपल्स में है that we can find out here. और वो कितना मल्टीपल है, accordingly we can see the tripping time. Okay, so for 10 times, so we can check on this vertical line, so which intersect at this instant on x-axis. So there is a 3 seconds, means when the 10 times current it is flowing, तो आपका रिले 3 सेकंड में ट्रिप हो जाएगा. एंड दिस इज डिफाइंड फॉर TMS इज इक्वल टू 1. TMS इज इक्वल टू 1 है ना. और हम लोग चेक कर रहे हैं TMS इज इक्वल टू 1 के लिए है ना, टाइम मल्टीप्लायर सेटिंग 1 के लिए चेक कर रहे हैं. व्हेन देयर इज अ 2 टाइम्स करंट, 2 टाइम्स IF fault current is equal to 2 times the set current IS. So आपका रिले 10 सेकंड में ट्रिप होगा. Now for this 2 times means 2 multiples. So for this line we'll check here, and this intersect at this horizontal line, and here you can see the time is 10 seconds. ये सब we are checking or we are finding out this time period for TMS is equal to 1 when time multiplier that disk it is a set at 1. Okay, now for 5 multiples, so it is a 4.3, 5 multiples, so this line, so here we can see 4.3. See, this is 5, this is logarithmic scale, so this is 4.3 seconds. Okay, so in this way, with the help of this standard curve, we can test this relay by injecting the current in the multiples of set value. Okay. So this relay can be tested on primary side or on the secondary side. So on primary side, we need, say your city secondary is 400 by 5 ampere, and we have to test this relay at TMS is equal to 1 for plug setting multiplier of 2. So we need to inject the 800 amperes of current through this primary side. And if we test this same relay on the secondary side, so we need the current of 10 amperes for 2 times. And if we test this relay for 20 times, so we need the maximum current of 100 amperes. This is for secondary injection. And for primary side, so 400 multiplied by 20. Okay, 4 2s are 8 and 3 0. So we need 8000 ampere primary side. So generally these relays, they are tested by the secondary injection method, where we need the maximum current source of 100 ampere to test the 20 multiples of current. And after this 20 multiples of current, so your tripping time is 2.2 seconds. Means 20 के आगे आपका fault current होगा, so it will take the 2.2 seconds for the tripping, and that time it is a constant. So it is called as an inverse definite. From 2, so it is a inverse up to 20 multiples, and after that, so there is a fixed or definite tripping time is there of 2.2 seconds for TMS is equal to 1. Okay, so in this way, with the help of these characteristics of the relay, we can test the relay by injecting the current in the multiples of set current of the relay. Now for that, we'll see one example. Say for this, we can find out set current as 5 multiplied by 2.5 multiplied by 0.5. Okay, so with the help of this equation, we can find out IN is a 5 ampere, M1 is a 2.5 ampere, and M2 it is given 0.5. It is a constant. Okay, so this is given on the nameplate, and it becomes 6.25. And in terms of percentage, this is a 125% of the set current. IN normal current. Normal current का ये 125% set हो गया. Now how we can test this relay? So we can inject the current in multiples of 6.25. Okay, so 6.25 multiplied by 2, 6.25 multiplied by 4, 6.25 multiplied by 5, 6.25 multiplied by 10. Okay. So from this we can find out the current to be injected to the relay. So it is 12.5. 4 means it is a 25 ampere, and this is a 31.25 ampere, and here 62.5 ampere. So this current we are injecting through the relay coil, and we are noting down the current at TMS is equal to 1. We set this TMS at 1 and we note down this tripping time. For 2 times it is a 10 second. It is 10 second. For 4 times it is say 5 second. For 5 times it is 4.3 second, and for 10 times it is 3 second. Okay, so in this way we can calibrate the relay, or we can test the relay by setting this time multiplier at 1 and injecting the current in the multiples of set current. Okay, so in this way we can test the relay by injecting the multiples of current of the set value by keeping this time multiplier setting at 1. Okay. Now if the plug setting is say 50%, it is 50% of IN means 2.5 ampere is a set current. 2.5 ampere is a set current, IS, and we inject the current in the multiples of 2.5 ampere. Okay, in the multiples of 2, 4, 5, say 10, 20, and we note down the tripping time of the relay. We note down the actual trip time of the relay. Okay, and if there is a change in the time, so we can set this relay to give the appropriate tripping time of the relay. Okay, so it must operate in the given time by the characteristics. Okay, so in this way we can set, or we can test the relay for various percentage of plug setting, various time multiplier setting. Okay, now for this 10 times at TMS is equal to 1, so it takes 3 seconds to trip. Now if we change this TMS to 0.5, okay, so our trip time should reduce to 1.5, okay. So because this 3 multiplied by 0.5, so at TMS is equal to 0.5, we verify this time on the characteristics, okay, for 10 times. So we can check or verify on this vertical line. So here this is a TMS is equal to 0.5, so this is a operating time. So here we can check the time period. Okay, so here we can get the 1.5 second. So this is a logarithmic scale. So in this way, by changing this time multiplier setting, we can change this operating time of the relay. Now we'll see the technical specification of this relay. When we have to select the relay, so what are the standard ranges available? What different parameters we must have to specify? First, we must have to specify the city secondary current, IN, normal current. Okay. Generally, the 1 ampere and 5 ampere, these are the two standard ranges of the city secondary. Okay. Say 400 by 5 or 1 ampere, 1200 by 5 or 1 ampere. Then after that, you must have to specify the system frequency. And as we see in the previous diagram, for 50 Hz and for 60 Hz, the tripping time, they are different. Okay, so for that we must have to specify the system frequency. And then current setting range for 5 ampere, so it is from 2.5 to 10. For 1 ampere it is from 1 to 4. For 1 ampere it is from 0.5 to 2. Means for overcurrent relay it is from 50% to 200%. 200%. Okay, so this is the standard range available. Then pickup current of the relay should not be greater than 130% of the plug setting. Then reset current, it should not be less than 95% of the plug setting. Time setting is available from 0.1 to 1, adjustable with the 0.05 calibration markings. When accuracy reference, so IEC 60255 standard, it is a referred for the IDMT over current relays. Okay. Then thermal withstand. Thermal withstand. So this primary coil must carry the current, continuous current without heating. So for that, the continuous overload current is 2 times the set value. 2 times the set value. Okay. If this current sustains for the longer time duration, so your primary coil, it may get damage. Okay, so this is for a short duration. Okay, for fraction of second. Then frequency 47 Hertz to 51 Hertz plus 9% to minus 4%. Then current setting 100% of IN for overcurrent and 40% of IN for earth fault current. Here there must be a 200%. Short time overload 50 times of the set current. 50 times of the set current for few milliseconds. Then burden, we must have to specify. This burden is required to calculate the burden of the city secondary. Burden is nothing but the VA consumption of the primary coil. Then how many output contacts are available on this relay, that you must have to specify, whether this contact should be self reset or hand reset. The current carrying rating of these output contacts, 5 ampere at AC or DC supply system. Then make and carry current for these output contacts. When the contacts they get closed or when the contact they break, they open, so maximum 20 ampere current for AC or DC supply system for 0.5 seconds they can withstand. Okay, indication means flag, it is reset flag, hand reset, manual reset. Okay, so these are the technical specifications of this overcurrent relay that we must have to specify or verify while designing the relay or purchasing the relay. So again, for this 2TJ relay, and say here 5 ampere CT secondary, 50 to 200% overcurrent, 5 ampere for earth fault, 10 to 40%. Then hand reset flag, it is given. The characteristics normal inverse 3 seconds. So these are the various parameters mentioned on the overcurrent relay, or that we must have to specify. So thank you for patience listening.